Recorded, rolling. It's Tuesday, January 27th. Yesterday, you guys collected data for this pendulum lab. Right, so you guys have your data out. Today, we'll go over what an ideal write-up would have been. We're going to put these graphs together in the back. I'll have you guys volunteer your data. And then we'll draw some kind of conclusion. We should have about 15 minutes at the end of class. I can get you guys started on some notes. And we'll show you guys some class examples of some of these AP classroom puzzles, for example, that are open that you guys can solve. Guys, when are you guys going to have the AP classroom puzzles finished by? Yeah. So February 4th is a Wednesday. I want to debrief those in class, so you guys will have those done by then. Right, so, yeah, probably tonight, I bet you guys can start looking at these questions. You can probably answer some of these questions tonight even. Okay? Your guys' last quizzes have returned, so before you guys leave for lunch today, you guys can pick those up out of your folders and, of course, do corrections, the whole thing. All right. So you guys ready to switch over to lab? All right, so here's the premise. That I got this pendulum set up. So I'm taking one of these lab weights, put it on a string, and pulling it back some angle from the vertical, let it go, and it takes some time to swing back and forth. Now, how much time does it take, and what variables could govern that motion? Okay. Now, we came up with this list of variables that maybe we want to investigate. Okay. So we're going to relate everything to time period. Okay. So the starting angle, this mass of this bob, and this length of this string. Okay. Now, gravity field will also be a variable, but we'll can't really tell for that. So we'll should just treat that as a constant. Okay. Okay. Now, guys, if you want to test three different independent variables and relate it all to this time period t, you really need how many different experiments? Yeah, three unique experiments. Now, I had you guys do all three unique experiments yesterday, and then I had you guys for AP just do a write-up on one of these three. So, yeah, I know it's been a day, and you guys have lots of class going on, so remind you guys what you did yesterday. Okay, so this table here, I have, maybe I was treating the length as the independent variable. Now, if I was doing that, then the mass and the angle would have been controlled. So maybe 50 grams all the way down and like 30 degrees all the way down, for example. Okay. Well, why do I have two different time columns? Times of 10, times of 1. Because what was that about?
Just to see like how much it is.
Yeah, increased accuracy. Okay. Guys, if you try to time one oscillation from the left side, and what is one oscillation? Is it from left side back to the left side again? Yeah. Okay. So if you try to time that, guys, suppose you have an error of like 1 second, 1 whole second. Okay, that's a pretty big error. Okay. But what if you let it swing back and forth, say 10 times, and then you divide by 10? Doesn't your error of 1 second also get divided by 10? Okay, so now it's way more accurate. Okay. Or maybe you did 5 cycles. I suppose some teams do 5 cycles yesterday. That's fine, okay. You do 5 and then divide by 5. Okay. Okay, so that was one experiment, is to change out the length. Another experiment is maybe you could change out the mass, which looks like this is what's going on here. So the mass increased. Looks like they went with grams on this paper. But you would want to lock in the length and also lock in the angle. So those would be controls. Okay, then see what happens with time. And the third experiment is maybe you could change out the angle. Go 5, 10, 15 degrees. So okay. Now, what I think I was telling you guys yesterday is that, guys, for this particular setup, I don't really recommend going much above 30 degrees. Once the angles get too big, the physics is a little wonky. I know some of you guys actually were testing bigger angles, but which is fine. Yeah, that's a good scientific thing to do. But when I plot graphs, if there's an angle that's like 70 degrees, then it might not exactly correspond to the textbook equation. All right, so you guys good with what we're doing so far? Right. So guys, have your write-ups out, and I'm going to go through a scoring rubric, and we're going to score these. There might be a colored pencil within reach. If not, just go ahead and pick up a pencil or pen. Okay, and all right, guys, I'm going to take you guys through an ideal scoring rubric, so you guys can get in the mind of an AP grader. Okay, now this is going to be altogether out of 12. What we're going to do is this: we're going to go through the first 8 points, which will take us through the procedure. Then we'll switch over to the graphs. Then we'll come back to this, and then we'll do the analysis points. What we'll do. Okay. And so the question is, what's the relationship between time period, capital T, so capital T is time period, and some other variable for a pendulum and simple harmonic motion? Now, you may have picked length. That would have been a good choice. And that's exactly the rubric that you're seeing right here on the screen. If you picked angle theta, then you can put angle theta here. If you pick mass m, you can put mass m here. Remember, I just wanted you guys to do one of these write-ups. So a write-up for one of the 3 experiments that you did yesterday. Okay. So again, I'm showing you guys T versus L, but switch the appropriate variables for whichever one you pick. Okay. So measuring tools. Well, if you did pick T versus L, you definitely want a meter stick or ruler to measure the differing lengths of the strings, and also a stopwatch or timer to measure the time. Actually, everybody better have a stopwatch or timer. Everybody was definitely using that. Okay, you guys got that? Now, if you were changing out the angle, I would definitely mention the protractor. And if you chose to change out the mass, it's probably a good idea to mention either a scale or a triple beam balance. Okay. All right, so far we're up to 2 points. All right, so everybody has a stopwatch or timer, and then one other tool depending on whichever was your independent variable. All right, procedure. So verbally go over what you should see in procedure, and then I'll show you guys that that's what it is. Right? Guys, AP is always looking for the same thing over and over and over. They're looking for a very brief description of the setup, that'd be a couple sentences, right? Followed by what variable did you measure with which of these each of these measuring tools? What was your independent, dependent variable controls? Right? And also mention multiple trials to reduce experimental uncertainty. That's always part of these AP scoring rubrics. You guys have seen many of these. Yeah.
Does AP allow you to put like step 1, step 2, step
3? Yeah, you can do that. Step 1, step 2, step 3. In fact, that would be pretty good, right? Because if you break it down, step 1, step 2, step 3, now that's really clear to the AP grader. Versus if you shove it all in one paragraph, it's a little harder for the brain to process, and they got hundreds of these that they're grading, right? Kind of imagine. Right? All right, so let's see procedure. Right, again, I'm showing you guys an ideal rubric here. So 1 point for describing setup. You should have a setup. It doesn't have to say exactly word for word what mine says, of course, but as long as it describes it. So here's what I would have said: connect a lab weight with known mass to one end of a string with, and the string has negligible mass, right, compared to the lab weight. Connect the other end of the string to a stable stand to create a pendulum. Pull the lab weight back so many degrees from the vertical and release it so the pendulum swings back and forth in oscillating motion. Boom. That's it. Right. Describe the basic setup. Right. We're just creating a pendulum, let it swing back and forth. Right. All right. And then what variable are we going to measure with what measuring tool? So measure the length of the pendulum from pivot point to the center mass lab weight with the meter stick, or you can set a ruler. Right. Measure the time for 10 oscillations with a stopwatch. And it's probably a good idea to also throw this detail in here somewhere. Determine the time period for one oscillation by dividing the time for 10 oscillations by 10, or you can do 5 and 5 or something like that. Okay. So we got the meter stick, we got the stopwatch. Okay. Now, if yesterday the write-up you went with was changing the angle, then you want to say measure the initial angle with the protractor. Right. If you said to change out the masses, and you want to do that write-up, you'd say measure the mass using the scale. Okay. All right, so you can switch out this first point depending on what your write-up is. Is there any questions so far? You guys follow what I'm saying? Okay. All right, let's go then. All right. Oh, multiple trials. Repeat the previous step 2 more times and find an average. Okay. You probably didn't actually have time to do that yesterday, right? But you would want to put that in an AP write-up as if you did, right? Like ideally, if you had 3 hours to do this class, you say, okay, I'm going to do 3 trials with a 50 centimeter long string, and then 3 trials with a 60 centimeter long string. Okay. What are we changing here? What are we keeping controlled and so on? So let's identify that independent variable. Okay, so this particular write-up is saying change the length of the pendulum and repeat the process. Do this for at least 5 different pendulum lengths. Right? So if you chose for your write-up, same experiment I'm doing, and you want to write that. Okay? If you chose to change the angle, you want to say change the angle to by 5 degrees every trial, and do this for 5 different angles. If you chose change the mass, you'd say change the mass every time and do this for 5 different masses. Right? So what I'm highlighting right there could be one of 3 different setups depending on which experiment you're writing up. Identify where are the controls. So for this particular experiment, I'm controlling the mass and also the initial angle. Right? And then if you did one of those other experiments, you're swapping out what your controls are. Okay? Yep. Oh, yeah. Right here. Yeah. Okay. So far we're through 8 points, and there are 4 more points. Yeah. So you guys are up to 8 right now, right? You guys are up to 8 points. Yeah. Right. All right. So the next step's going to be the next part's analysis and then conclusion. But to do that, we got to get the graphs. So let's put these graphs together. All right. You guys ready to get some graphs together? Yeah. Graph time. Yeah. All right, so of course you guys got a table. If you flip the table over, then there's space for 4 graphs. Right, so let's do time period in seconds as a function of, let's start with angle. let's do angle theta, and let's stick to degrees. Okay? Now, side that here is if there's some kind of funny relationship that opens up, like for example, if you increase the angle and you saw an increase in time period, right? Then I would want to do one of two things with this theta to actually makes like real sense of this. I'd either want to switch this to radians, or I'd want to fit this inside a sine or a cosine function. But let's just start with degrees, plot the points, and see what happens, and then we'll be able to navigate from there. Okay. Right. And I had you guys hypothesize yesterday, but now you guys probably know the answer. So, guys, as you're increasing the angle from say 10 to 20 to 30 degrees, what happens in time here? Who thinks they have some pretty good data they want to share? Pretty good data. All right, how about Felipe? Felipe, what was the largest angle you guys used?
90 degrees.
Okay, now you guys did go up to 90. So I'll go ahead. Let's go ahead and plot the points, see what happens anyway. Let's go 0, 10, 20, 30, 40, 50, 60, 70, 80. Here's 90 over here. Okay, 10, 30, 50, 90. Okay. So you guys see, just like always in this class, I'm going to start at 0 and scale linearly. All right, so we'll start with that. Now, remember too, I'm not going to completely trust anything past about 30 degrees, but we'll just see what happens. Right? And what was your longest time period?
Sorry, what'd you say?
What was your longest time period?
The longest time period, we got 1.872 seconds.
Okay, 1.8 seconds. So I'm gonna scale this 0, 1, 2 seconds. So 0, 1, 2. Right. Of course, some of what probably goes into this time period is not just the angle. It's of course some established length. Do you have a length recorded for that?
Length,
Yeah, what was the length on this pendulum?
we got 0.62.
Okay, so they're using a 62 centimeter long pendulum, right? And that was one of their controls for this one. All right, let's get some points. What's one coordinate?
So one coordinate is 10 degrees
10 degrees?
and 1.68 seconds.
1.68 seconds. That's
Yeah.
right about there. Bam. That point on the board. Right, next coordinate.
I point one to that.
Huh?
20 degrees and 1.672 seconds.
1.672. Bam, right there. Next coordinate.
5 degrees and 1.62 seconds.
5 degrees, 1.62. Bam. Right, next coordinate.
15 degrees, 1.69 seconds.
1.69. Bam. Next coordinate.
25 degrees, 1.67 seconds.
0.67. Bam.
Uh,
You said 25 degrees?
yeah, 25. And we got 50, 1.694 degree. Oh, seconds.
Bam.
Yeah. In 90, we got 1.872 seconds.
Ooh, well, okay, so that one jumped up a little tiny bit. So bam, right over there. Okay. Yeah, okay. It is really good though that most of the angles you chose were kind of fairly on the small side, up to about 30 degrees. Okay. So, guys, looking at that data right there, you guys know, pull up this page about every lab, and these graphs you guys want to know for this particular class. Okay. Which basic relationship do you think that is? Yeah, no relationship at all. Okay, because looks like it doesn't matter what the angle was for that particular pendulum that was, you said 62 centimeters long. It looks like it takes about roughly 1.6, 1.7 seconds to oscillate back and forth. Right? No matter the angle. Right? Right. So I think by the time we come up with some master equation for what's going to govern the motion of the pendulum, do you think the angle has anything to do with the time period at all? No, it's not even going to show up in the equation because there's no relationship. Let's spell that out. No relationship between time period and starting angle. Okay. All right, so let's try a different variable. Let's say what's the time period as a function of mass. All right, let's do switch out masses. All right, who thinks they have some pretty good data for masses? All right, how about
Use your data, bro.
so what you got?
For our
Yeah, what was your largest mass?
1 kilogram.
One kilogram. Right, bro. Okay. Alright, so let's just go ahead and call it grams right now. Because really I'm just looking for proportional relationships, and I'll call it 1,000. Because 1,000 grams per kilogram. So this could be 500 right here. 1, 2, 3, 4. 2, 3, 4. Okay, 0, 100. Okay. All right, what was your longest time period?
1.71.
Right. Okay, so I'll scale it the same as before. 0, 1, 2. So this is time in seconds. I got 0, 1, 2. All right, so all the data should fit right here. All right, let's get some coordinates. What's one coordinate?
0.5 to 500 grams and
Okay, so 500 grams to 0.5 seconds.
1.69.
Oh, 500 grams to 1.69 seconds?
Yes.
Okay, that's right about here. Bam. All right, what's another coordinate?
100 grams to 1.62 seconds.
Ooh, almost the same time for 1/5 of the mass. Bam, it's right about there. What else you got?
1,000 grams to 1.7 seconds.
Huh. Same time. All right, what else you got?
200 grams to 1.5 seconds.
0.5. Or wait, what? You're saying 1 point something?
1.5 seconds.
I'm so sorry. Here, I messed up my scale. That's all right. That's all right. I'm just gonna put 1 here, and I'll put 2 here, and then this could be okay. All right, so now we're back. I don't know why I was cut off the 1. Sorry, can you read that last coordinate again?
200 grams to 1.5 seconds.
1.5. Okay. Yeah. Sorry, my scale's off a little bit, but okay. What you got?
And then 300 grams to 1.4 seconds.
0.4. Yeah. Okay. Oh, you have another?
20 grams to 1.4.
20.4. So right here. Okay.
10 to 1.4.
Okay. All right. I think we're getting a pretty good story here. So, guys, what does that look like, you think?
No relationship.
Also, no relationship. Also, no relationship. Okay. So, yeah, it turns out also it doesn't matter which mass you use for the bob. Yeah, it's taking the same time swing back and forth too, right? But you know what? It's actually consistent with the story that I've been using throughout the school year. Okay? Do you guys remember Galileo runs to the top of the Leaning Tower and he drops both of these? And they fall side by side all the way down. Well, guys, if you just attach a straight to them, turn them into pendulums, I think it's the same kind of effect. Right? The one on my left hand has more weight, but it also has more inertia. Okay? So more weight, but also more inertia. Right? And the two effects cancel out. So in a gravity field, they sort of have the same type of motion. Yeah, that's completely consistent with that, isn't it? Right, you guys get it? Huh. So far we got no relationship, no relationship. Well, it's gotta be something going on. So let's do time period in seconds as a function of length, and I'll let you guys tell me the unit. And so who has pretty good data for length pendulum? Who wants to do length?
Richard?
Richard? All
Yeah.
right.
No, Jonah said
Richard, what?
Jonah really wants to.
All right, Richard, what's the longest length? Longest length.
We unfortunately we did not do length.
Oh, did you like?
No,
Okay. You got some data? Yeah, what's your longest length?
Yeah, we saw that Richard has length. Richard has length. Oh, Richard has length.
Oh,
Yeah.
you got length?
We got length.
You got it?
That's cool by me.
All right, what's your longest length?
It's so much 0.5
About what? Okay, so it sounds like we're going in meters.
meters.
All right, so let's go point 1, 2, 3, 4, 5. So 0, point 1, point 2, point 3, point 4, point 5. All right, and then a little about that. And what was your longest time?
1.51.
1.51. Okay, so let's go 0, 1, 2. All right. Okay. Let's put this together. What's one coordinate?
0.51, 1.51.
1.51. It's right here. Bam. All right. Next coordinate.
0.46, 1.41.
46, 141. Bam, right there.
0.35, 1.29.
129. Bam.
0.31, 1.19.
Bam.
0.26, 1.1.
1. Bam.
0.18, 0.99.
Bam.
0.09, 0.73.
7, 3. Probably there.
Well,
Bam.
looking like it's something.
That was it.
Ooh, yeah. Something exciting going on. Huh.
I think it.
Oh, what do you?
I think it's a roof.
Let's see. Show of hands. Show of hands. Here, I'll narrow it down to. I mean, it's probably one of these, isn't it?
It doesn't go to 0, so it's not linear.
Maybe that's a hint. Show of hands. How many guys think? Oh, that looks linear. Who says linear? Nobody says that. How many guys think it's probably this one? Yeah. I think it's, or I suspect this is going to be a square root.
Mr. Griff, are you proud of me?
Sure am. Yeah, you guys are all grown up. Yeah, got sent out from the moon.
It's fine.
Yeah.
This is.
So it's probably, I'm suspecting time period proportional to the square root of length. Okay. Now, guys, what we're going to do next is go back to the table. You guys remember I gave you guys some length columns? You guys remember that? Okay. Yeah, let's just do this way. Guys, let's do time period squared. And the unit's going to be square seconds. Guys, go ahead, write out. Everybody go ahead and do this. Okay. So square all your time periods. Okay. So if for example, if it was 0.8 seconds, 0.8 squared is 0.64. Okay, and that'd be square seconds. Okay. So go ahead and do that. Okay. And while you guys are doing that, okay, for the video here also, I'll remind you guys what we're about to be doing. Okay. The last graph we got says time period is some constant times the square root of L, or at least it looks like it's probably that. Or you could write it this way: time period proportional to the square root of L. Okay. Now there's two different, like guys, if you had a square root curve, doesn't this K represent like sort of how curvy the curve is, like vertically stretched? Here, guys, think about this. Okay. I know we've done this a few times, but I think it's worth thinking through again. Okay. But how do you figure out how curvy is a square root curve? Like, what is this K here? And a really efficient, effective way of doing that is to linearize the graph. You guys remember linearization?
Mm-hmm.
And there's two different ways you can linearize this. And we're just going to do one of them. But you guys tell me one way. You could graph what versus what. It's not T versus L. It's going to be what versus what.
L versus T squared versus L.
Yeah, T squared versus L. Actually, that's the one I'm going to do with you guys. Right? Because, guys, if you pick up from here, if you square both sides, couldn't times squared be proportional to the length? Right? Now, these points should all line up in a straight line. And then, can you find the slope of the line? Do you rise up or run? And then that can give you an equation. Okay. There's another way you can do this.
Do we have to make a T squared column now or no?
Yes. Yeah. So you make T squared column. Right. You're squaring all your times because I'm about to get those from Richard, and we're going to make a new graph.
Richard's fine.
Now, another way to also linearize the graph, you could have done, guys, could you do T squared? Sorry, T versus what?
I think we should get Richard around.
Probably seriously. Yeah. Could you guys keep do a T versus square root of L? Would that also linearize? Yeah, it sure would. Okay. Let's do it this way on the left. So we're going to T squared versus L. Everybody see what we're doing? Why? Alright, so let's do that. Do that. So I'll go T squared, and it's going to be a square seconds. Okay. Now, the biggest time before was a little less than 2 seconds. T squared is 4. Let's go 1, 2, 3, 4. So 0, 1, 2, 3, 4. Okay. And I'm going to leave the length axis exactly the same as before, in meters and so on. 0.1, 0.2, 0.3, 0.4, 0.5.
You guys want raise?
All right. So now I have a new set of axes. All right, Richard, you got the new coordinates?
I don't.
Why?
Oh, where's the paper?
The same coordinates.
Okay. Yeah, guys. So we're taking the exact same data you gave me for this curve. You just square all the times.
Yeah,
All right, do you have a calculator? Let's just do it as we go along.
It's loading.
Loading.
Yeah.
What? Did I give you a handheld calculators?
Richard.
I was using Desmos.
Okay. This one loads in like a second. So, all right. We're gonna square all the times. We're gonna square all the times. We're gonna plot these. I bet these points line up in a straight line. It goes through the origin, but we're gonna find out. Okay. All right. So what's first coordinate?
0.0 5. Wait.
Yeah. So
1.51. Wait, no.
Oh my god.
Wait, what are we? Oh, wait. 0.51.
Uh-huh.
2.28.
So 2.28 is the times square. That sounds about right. 2.28. That could be right about here. Okay, you can go leave what? 0.51 comma 2.28. This is meters. And this is square seconds.
Go down a bit.
0.46.
0.46.
So T squared.
1.77. 1.99.
1.99. Ooh, right about there. Okay, next point.
0.35. 1.66.
1.66. Right about there. Bang.
0.31. 1.42.
1.42. Bam. Okay, next point.
0.26. 1.21.
1.21. Bam.
0.18. 0.98.
1.8. Sorry, can you say it again?
0.18.
Huh?
0.98.
Bam. Okay.
And then 0.09. 0.62.
62. That's probably right there. Bam.
So
Okay, so label that. This is 0.9, 0.60. This is meters and square seconds. Okay. Oh yeah, look at that.
That's looking linear to me.
That does look pretty much a direct relationship, doesn't it? Yeah, it's pretty much a direct relationship. Okay. But now guys, if we found the slope of that line, we could very quickly get a pretty good governing equation. Right. And then since the angle and the knots don't matter, you could describe how any pendulum is going to swing in Earth gravity. So let's get the slope. Now, guys, ideally what you do is you pick 2 points on the line. I'm going to flesh this a little bit. I'm just going to pick the first and last coordinate, which is going to underestimate a little bit. You guys see this coordinate's a little bit above the line, this one's a little bit below. Right. So it might underestimate it a little bit. That's okay. Because just for class. Right. If this were a FRQ, you'd want to pick 2 points that are up and down the line, not necessarily the coordinates themselves. So what we have here is time squared is equal to the slope, I'll call slope k, times L. So what is this k, the slope right here? Well, that would be change in time squared over change in length, which is, let's see, 2.28 minus 0.62 square seconds. And that many meters. Right, so let's see. 2.28 minus 0.62 over 0.51 minus 0.58. No. Sorry. Point oh.
5 minutes.
Whoops. Whoops. That's 0.09. 0.09. There you go. That makes more sense. Pop a 0 in there. There. Better. Oh, okay. Okay. K is 3.95. That's square seconds per meter. That's what that would be. Right, so you guys get?
Yeah, no, I'm
Okay, so then the exact equation can be time period squared is equal to 3.95 square seconds per meter times length. Okay. Or alternately, E equals something times the square root of L. Okay. Hey guys, how do I find this number right here? Guys, what you think critically? Guys, is this going to link to the actual textbook answer I'm about to show you guys? But I want to see if you guys can get this. Okay. Here, we went through t squared and we got this expression. Is that okay? Where I got this from? This box?
Oh.
Right. But now that we have this, what if I just went the time period just straight up in terms of the square length? How do I get this number right here? Square root of this. Yeah. Right. And on the calculator, see if you remember this. Guys, if I want to take the square root, can I do to the power of what? Yeah. Okay. So that's like 1.99. And that'd be seconds over root meters.
I don't
times square root of. Like that. I got it. Okay, so this equation, the same thing. Okay. All right. You guys ready to see the textbook solution? Textbook solution.
Sensei.
Huh?
You're Sensei Griffin.
Right. So here's straight from textbook. Again, if the theta is about 30 degrees or less. How much time it takes to move back and forth has nothing to do with this angle. Has nothing to do with this mass. Okay. Yeah, length matter. Oh, see square root of the length. We figured that out. We graphed that. Earth gravity matters. Couldn't really test for it, but guys, does it make sense that you'd be dividing by gravity? Okay. Like here, guys, if you went to the moon, how does moon gravity compare to Earth gravity? Very, very small. If you divide by a small number, the time period becomes very what? Large. So on Earth, if your pendulum was going swing, swing, swing. If you went to the moon, would it more like
Be slower.
yeah, it would take more time, wouldn't it? Does that make sense? Okay. Now, if we put these side by side here, we got here, time period, straight from textbook. We got 2 pi times the root L over G. Right. Well, guys, if that G was a constant for this class, guys, write this down. Can I take that root G and slide it over and say this is 2 pi over the root G times the root L? Is that? Okay. And, all right, you guys ready for a moment of truth? See if this all comes together? Okay. If your data was exactly correct, what should, guess who I just circled in peak right here?
Yeah.
If I run that in my calculator, what number should be very, very, very close to? About this number right here? This number right here?
Yeah.
You guys see this and this take the same place? You guys see that? Does anybody not see that? See that? All right, let's try it out. 2 pi. Try this with me. 2 pi divided by square root. And what number goes here for gravity field? Yeah, let's try it out for you. It's even more precise, isn't it?
9.8 meters per second squared.
And you guys did give me lengths and meters, so we don't have to do any unit conversion. Let's see. All right, let's find out. Is it 1.99? Oh yeah! Oh yeah! Look at that! Wow! Wow! You guys did a great job. Oh yeah! You guys see it? Yeah. Okay, guys, let's cover physics. So let's switch back over to the scoring rubric. All right, so you guys got your lab write-ups out? Lab write-ups? All right, so far we've done 8 points. We're through the procedure. Let's go to analysis. Hey guys, analysis. If you're trying to solve for something specific, sometimes they want you to break out equations, but oftentimes for these bigger labs, they're looking for for graph properties, and more often than not, something like the slope of the line or something. But let's see what we're going to do here. All right, so graph t versus L on a set of axes. The graph displays a square root relationship. Therefore, square all the time periods and graph t squared versus L, and the graph will show up as linear. Right? Now, by the time you guys take the AP exam in a couple of months here, you will be expected to know how this is going to work out. Right? You'll have the equations running. Oh, I need to show you the equations too from the AP page. Yeah, before you leave class. But here, we've got some things to finish here first. Yeah, you'll eventually turn this in. Right. Say here, t squared versus L, graph's linear. Okay, so you would know it would play out like this. Okay, guys, if you did a write-up yesterday for one of the other 2 experiments, then, like, guys, if you pick t versus theta, then what's the answer to that again? T versus theta would be no relationship. If you pick t versus m, that would also be no relationship. So if you pick that, you just say no relationship, then go ahead and give yourself full credit, right? But if you pick t versus L, you really need to do this followed by this and this, right? Or you could have said graph t versus the square root of L. Would that also linearize? T versus the root of L? Yeah, it could have done that way too. Right? In fact, that's the last thing we were just looking at. Right? All right, and then conclusion. So t squared is proportional to length, or t is proportional to the square root of the length. Okay. Or if you did one of those other experiments, time period is not it has no relationship with either the angle or the mass. Yeah.
So for both of these, if you didn't do T versus L, you would just have to say like no relationship.
Yeah.
Those 4 poles.
If you did t versus theta or t versus mass, your conclusion would just be there's no relationship. Yeah.
So yeah, you still get the point for just writing out like no.
Yes. Okay. Guys, the only scoring rubric I'm actually showing you guys is just for t versus L. But if you have one of these other ones, you can do a modification.
Is it fine if we did T versus L?
Yeah, you can pick any one of those three.
Alright.
Yeah. All right. All right. So you guys good on that? Guys good? All right. Switch back over here. Okay. So on your AP equation page, AP equations. Let's do here. I think it's a pretty good one right here. Right here. Alright, so I'll show you guys the set of equations that we're going to be looking at for this week and next week. Okay, then what? Alright, so guys, it's these 5 equations right here. So here's all rotational mechanics. So these 5 right here. Go ahead and circle these 5. Now, the posters I have are yellow banners, so I'll color the yellow. And these are going to be simple, harmonic. Yeah.
What are we doing now? Am I missing anything if I use the?
I'll make recording notes. But here, I'm recording it.
Alright.
Okay, so here, take guys a quick run through these, and then I'll switch over to my poster versions of these.
Thank you.
So, what do you guys think this top one refers to? T is 1 over F. What do you guys think that means? What do you think the T stands for? What do you think the F stands for? Exactly. Yeah, time period and frequency. So turns out that time period and frequency are just reciprocals of each other. Guys, if time period is 1 over the frequency, then what do you think frequency is in terms of time period? Yeah, also 1 over T, like that. Okay. So if this is true, this is true. These are reciprocals of each other, aren't they? Okay. Guys, let's do a numerical example. So this will click. Okay. Guys, what if the time to swing back and forth for your pendulum, the time, let's say it took half a second. Do you guys get that? It takes half a second. Guys, what is 1 divided by 0.5 seconds?
2. 1.
Yeah, it'd be 2. And some of you guys might know this too. What's the unit for frequency? Hertz. Yeah, it is hertz. HZ, which stands for hertz. Okay. Which is the same thing as cycles per second. Or you could just say 1 over seconds, which we're looking at here. So 1 over 0.5 seconds is 2. Oh, and guys, think about what that means for the example I just told you. Guys, if it takes half a second to cycle back and forth, then after another half a second, hasn't it cycled twice? Oh, hence 2 cycles per second. You see that? Right. And then vice versa. What if you had a frequency of 2 hertz? 1 over 2 hertz. I'd be telling you it takes how much time to cycle back and forth? Half a second. Half a second. Right? Guys, what if you had a frequency of 10 hertz? If the frequency was 10 hertz, how many times is it cycling every second? Or sorry, I said that the wrong way. Let me say again. Right. If you have a frequency of 10 hertz, it's cycling back and forth 10 times every second. Right. How much time does it take to cycle once? Yeah, 0.1 seconds. You guys get that? Right. What if it took exactly 1 second to swing back and forth? Would this be 1 hertz and this would be 1 second? Okay, so like that. All right, so that's all this one says right here. Okay. Now these next couple formulas, I'll show you guys with my poster version, right? And then these last 2 down here, do you see like a sine and a cosine? Right. So you'll also see that before you leave for lunch today too. Right. Right. So look at those formulas there. Okay. Let's go through these. Okay, so here's the conclusion to your lab. Okay. You guys got this relationship. Okay. Now let's do some proportions. Guys, what if I have a pendulum so length it takes some time, and then I'm gonna do this. Is what if I have a string that's 9 times as long? Guys, 9 times as long takes how many times to the time to go back and forth? 3. Because square root of 9 is 3. And of course, you can plug in all the numbers to try that out. But 9 times the length is 3 times the time. Is that the square root? Right. How about this? What if I go to a planet that has 9 times the gravity field? Ooh. Guys, 9 times the gravity field. What happens to the time period? 1/3. So it's now swinging back and forth faster. Okay. Now, okay, here's very similar to plot table you guys had. Okay. Here's the 4 graphs we just put. We just picked this 4 graphs. We just made all those. Okay. So know all these, of course. Okay. Ooh, this one's here's a little bonus. Now I did see your guys' textbook ask a question like this. I've never seen AP ask exactly this, but I want to do this once with you guys. Okay. Guys, what if you have a pendulum that's not this classic bob on a string? Right? Oftentimes they'll say like the string with negligible mass, blah blah blah. Right? But what if you had like a hanger going around a doorknob? That's not exactly this, right? You guys get it? It's a little more complicated. So let's look at how you solve that. So you have to go through the rotational inertia, and I think your textbook asked one specific question. Had you like, what if you have like a Christmas tree ornament, like a sphere that was going back and forth like this? You have to go do parallel axis theorem. But let's do it for what I want you guys to do, guys, look here, look here. You guys taking notes, right? Taking notes. Okay. Let's apply this point mass situation to this general formula and see if it simplifies to this. That's what I want to do. Let's do it. So I'll get t equals 2 pi times the square root. There's a fraction here. Now the denominator is like NVL, so go ahead and keep that. Okay. But guys, this I right here, I want to do it I for a point mass, as in the bottom of a pendulum, right here. Okay. Hey guys, let's go back a couple weeks ago in this class. What is the rotational inertia of a point mass? mr squared.
MR squared.
And isn't the r here like this L?
Yeah.
You guys get it? So what am I going to write right here?
MR squared.
ML squared. Yeah, ML squared. Okay, so what next? What simplifies? And what are you left with?
2 pi like is gravity.
Oh yeah, it's the same thing. It's the same thing. Yes, it's the same thing. Oh, right. Again, for this class, this is really the only one you have to like. All right, but you guys see that connection? Okay, so no, because there are two main oscillating scenarios that you'll see in AP physics. Right, one of them is of course the pendulum. Right, and the other main scenario, and I have a lab queued up for you guys for this one too, but you guys will kind of spoil the answer ahead of time. Is a block on a spring. You guys see this block on a spring? Okay. Now, ooh, guys, look up here. Look up here. You have to think about this. Okay. Now, this is another equation on your AP page. Okay. So they do block on spring here, and here's the pendulum. Okay. So you got both those right there. Okay. You guys see that they're really similar structure. They're both time period equals 2 pi times the square root of a fraction. Right. But what's inside the fraction is a little different. Okay. So pendulum, we got L over G. But the mass of the spring, we got the mass M. Okay. And guys, what does the K stand for?
Spring constant.
Spring constant. Like how stiff is the spring? You guys remember your spring scales had spring constants in like the hundreds of newton per meter? You guys remember that? Right. Just something like that. Okay. Guys, what about this? Guys, what if I take this spring right here? Guys, look here. Guys, focus. I'm gonna pull it back and let it go. It's gonna oscillate. Bow, wow, wow. It's gonna take some time. Now, guys, look up here. Now let's take this to the moon, which has very weak gravity, a little bit of gravity. And it's the same thing. I'm going to pull it the same like I did before. I'm going to let it go. How much time does it take to oscillate on the moon compared to Earth? You said what? Same. How do you know it's the same?
There's no gravity.
Because gravity's not part of this equation. Oh, that's interesting. Guys, what about this? What if I take this block on a spring and I turn it horizontal and I have a frictionless surface here? You guys see this frictionless surface? I let go. Is it the exact same equation? Yes, it is. Okay. All right. So anytime I'll have you guys do this lab, I'll give you guys some springs and some masses. So come up soon. I'll do that. Okay. Okay. And here's what's eventually going to be the results that you guys are going to find. Right now, what's this graph down here at the bottom right? This is a funny looking graph. Probably a cosine. You could also describe this with a sine. Right? It's like it's height versus time, or it's position versus time. Right? Which is like oscillating. You guys see that? Right, so let's dig into that oscillating motion. Okay. So guys, focus here. You have to think.
Locked in.
Okay. Right, so here's what I got a vertical spring and a horizontal spring. Okay. The vertical one's bouncing up and down, horizontal one's going right and left. You guys see that? Okay. No, let's look at this motion. Suppose it goes from end to end. So here's like the amplitude over here, and then it's being maximal compressed here, maximal stretched here. Okay, and the equilibrium point could be right in the middle. Equilibrium's here. Here's max stretch. Here's max compression. And it's also in between these two. Guys, which point here? Which point here is it moving the fastest? Guys, where do you think it's moving the fastest? I think right in the middle through the equilibrium point.
Yeah.
As it goes through the equilibrium. And if I did the vertical one, it'd be the same story. Right through the middle, it'd be moving the fastest. Okay. Now, out here, does it have zero speed? And out here, it's also zero speed. Okay. And between here and here, it's all tension. And then here and here, it's all in compression. Right. Right. So I'm watching it like reverse direction, speed up, slow down. Okay. If I also have a car that's going around this circular racetrack, and maybe I'm looking helicopter, look straight down. Sometimes you hear this called phase space. Right. It turns out that the x coordinate from this horizontal one, maybe it's like east-west coordinate, and the y coordinate, like the north-south coordinate for this vertical one, will exactly tell you where the car is going at constant speed around the circle. Okay. Which means that we could create ultimately these graphs. But before I show you guys these, I'm going to do one more building block into that. Okay. Okay, so here's frequency and time period. You guys got those? That's okay. Okay. Now, I'm going to introduce a new variable. You guys see this omega here?
Yeah.
Guys, focus here. Now, I know the last few weeks we've been calling that angular velocity, but that's not what this is. This is a special kind of frequency. So just take the regular frequency, 1 over the time period. Isn't that what f is? Just 1 over the time period? You guys know that, right? It's right here. And I'm going to multiply that by 2 pi. Now, here's why. Because I'm trying to ultimately craft a sine or a cosine to describe position versus time. Okay? But it's going to be really handy to use the special kind of frequency that's multiplied by 2 pi. Okay? And it goes back to the unit circle. So guys, let's do a unit circle review. Unit circle. Let's call this 0 radians right here. Guys, halfway around the circle, how many radians is this?
1 pi radian.
Yeah, pi radians, right, which is 180 degrees, by the way. But let's talk about radians. And 1 complete cycle is how many radians?
2 pi.
Yeah, 2 pi radians. That's 360 degrees. Call it 2 pi radians. Okay. Okay, so guys, if you made 1 complete cycle, that would correspond to 2 pi radians, right? So if I had a sine or a cosine of 2 pi, that would correspond to 1 complete cycle. Okay. So if you have a frequency of say like 10 hertz and multiply that by a time period of 0.1 seconds, that can cancel out. And if you bring in the 2 pi, that would be cosine 2 pi, and I've completed 1 full cycle. You guys see that? 1 full cycle? Okay. Okay. Well, here, we're going to have to close this recording today, but tomorrow we'll pick up from here and continue that.
Sure.